Imagine this. Two planetary destinations, each with its own mysteries and allure, Mars and Mercury. These worlds, though neighbors in our solar system, could not be more different in their appearance, their environments, and the challenges they present to explorers. One is a rusty red world, its surface dusted with iron oxide and marked by ancient volcanoes and canyons. The other is a scorched, cratered sphere, battered by meteors and baked by the relentless sun. At first glance, you'd think the closer planet, Mercury, would be the easier destination for our spacecraft. After all, it orbits just next door to the sun, while Mars lies farther out, a distant red beacon in the night sky. But space doesn't play by our rules. The universe is full of surprises, and the path between planets is rarely as simple as drawing a straight line. Here's the twist. It takes just 7 months to reach distant Mars, but a staggering 7 years to get to nearby Mercury. How can this be? What makes the journey to Mercury so much more challenging? The answer isn't simply about distance, it's about the invisible forces at play, gravity and energy. These are the true architects of every interplanetary journey. In space, every voyage is shaped by the sun's immense gravitational pull, which acts like a cosmic anchor, tugging at every planet and spacecraft. To reach Mars, we ride Earth's momentum outward, coasting away from the sun's grip. The journey is like being pushed gently down a slope, letting inertia carry us across millions of kilometers. But to reach Mercury, we must do the opposite. We have to fight the sun's gravity, slowing down as we fall inward, spiraling closer to the solar furnace. It's a battle against the very force that holds our solar system together. Imagine a cosmic roller coaster. To get to Mars, you coast downhill, gathering speed with ease. But to stop at Mercury, you must slam the brakes, fighting momentum and gravity at every turn. That's why the closer planet is actually the harder target. Mercury's proximity to the sun makes it a fortress, guarded by physics itself. This is the paradox of interplanetary travel, a journey shaped not just by distance, but by the invisible hands of gravity and motion. So, buckle up as we prepare to dive deeper into this cosmic puzzle. We're about to unravel why, in the vastness of space, the easiest path isn't always the shortest, and why our intuition about travel between worlds can be so misleading. Welcome to the story of Mercury versus Mars, a tale of two planets, and the extraordinary journeys required to reach them. Let's look at the numbers. When we think about traveling through the solar system, it's tempting to assume that the closest planet must be the easiest to reach. But as we'll see, the reality is far more complicated and fascinating. Mars can be anywhere from 55 million to over 400 million kilometers from Earth, depending on where the planets are in their orbits. Mercury, on the other hand, can come as close as 77 million kilometers. At first glance, you might think Mercury would be the obvious choice for a quick trip. But space travel isn't about straight-line distance. Instead, it's about the complex paths dictated by gravity and orbital mechanics. The shortest route on a map isn't always the easiest or fastest in space. Right now, Earth is racing around the sun at a staggering 107,000 kilometers per hour. That speed isn't just a fun fact, it's a crucial part of every journey we make beyond our planet. When we launch a spacecraft to Mars, we take advantage of Earth's momentum, swinging outward into a higher orbit around the sun. This means we're not starting from zero, we're already moving fast, and we use that speed to our benefit. Imagine throwing a ball from a moving train. The ball doesn't just move at the speed you throw it, it also carries the speed of the train. That's the boost our spacecraft gets when heading to Mars. But if we want to reach Mercury, things get trickier. Instead of using our speed, we have to fight against it. We need to slow down, shedding much of that inherited velocity to fall closer to the sun. Instead of speeding up, we're braking, firing thrusters in the opposite direction, working against the sun's powerful gravity. It's like trying to stop a runaway train, not just coasting to a stop. If we don't slow down enough, we'll simply fly right past Mercury, missing our target entirely. There's no room for error. Precision is everything. Slowing down in space takes enormous energy, far more than speeding up. Every bit of velocity we lose requires fuel, careful planning, and powerful engines. That's why a trip to Mars is often a quick, energy-efficient hop, while a journey to Mercury demands a long, complex process of braking, looping, and careful maneuvering. The path to Mercury isn't a straight shot, it's a winding, spiraling journey, often involving multiple flybys of other planets to bleed off speed and gradually approach Mercury's orbit. Each step along the way is about losing speed, not gaining it. The spacecraft must carefully time its engine burns, and gravity assists to slow down enough to be captured by Mercury's gravity. So, even though Mercury is closer to Earth than Mars at times, the journey is far more challenging. That's the core dilemma. closer isn't always easier. The sun's gravity makes Mercury a fortress, pulling everything toward it with relentless force. Getting close means fighting that pull every step of the way. Mars lets us coast, riding our momentum across space. Mercury, in contrast, makes us fight for every kilometer, every second, every bit of progress. This is why travel times to Mercury are often much longer and more complicated than trips to Mars, even though the distance can be less. In space, it's not distance that sets the rules, it's energy. The true challenge is overcoming the invisible forces that shape every journey between the planets. Imagine the solar system as a vast, cosmic rubber sheet stretched out in all directions, a fabric that bends and curves under the weight of massive objects. This is how gravity shapes the universe around us, warping space itself. At the very center sits the sun, like a gigantic bowling ball pressing down and creating a deep, central well in this sheet. Its immense mass distorts the space around it, pulling everything nearby into its gravitational embrace. The planets, from Mercury to Neptune, roll along the grooves carved out by the sun's gravity. Earth orbits in a gentle, wide groove farther from the center, while Mercury circles deep inside, close to the sun's intense pull. When we send a probe to Mars, it's like nudging a marble from one groove to another. Just a gentle push is enough to shift its path. The energy needed is modest, and the sun's grip is weaker at that distance. Out in the outer solar system, the sun's gravitational pull is manageable, almost gentle compared to the forces closer in. Spacecraft can coast along, using small bursts of energy to adjust their course. But reaching Mercury is a different story. To get there, we must send our spacecraft plunging down the steepest part of the gravity well, accelerating rapidly as it falls toward the sun's powerful grip. The sun's gravity doesn't let go easily. As the spacecraft draws closer, it's pulled faster and faster, gaining tremendous speed that must be carefully controlled. If we don't slow down at just the right moment, the probe will either slingshot past tiny Mercury, missing its target entirely, or spiral uncontrollably into the blazing sun. The real challenge isn't simply arriving at Mercury, it's slowing down enough to be captured by its weak gravity, which is easily overpowered by the sun's nearby pull. That's why, instead of speeding up, we burn precious fuel to slow the spacecraft, firing thrusters in a delicate balancing act against the sun's relentless force. Every maneuver must be precise. It's a delicate, energy-hungry dance, requiring careful planning and perfect timing to avoid disaster. Mercury's proximity to the sun makes it one of the most challenging destinations in the solar system. The planet's tight orbit and the sun's glare create a hostile environment for any visiting spacecraft. The closer you get to the sun, the steeper the gravitational well becomes, and the harder it is to stop. That's why reaching Mercury is a true test of engineering and ingenuity. How do you slow a spacecraft falling into the sun's gravity well? You can't just slam on the brakes, there's nothing to push against. Carrying enough fuel for one big burn is impossible. Instead, we use gravity assists, flybys of Earth and Venus to steal orbital energy and slow down. Each flyby is a precise maneuver, shaving off speed bit by bit. The MESSENGER mission used 6 flybys before finally entering Mercury's orbit. This slow, looping path is the only way to make the journey possible. It's a patient, strategic ballet, turning the solar system's gravity into our ally. Arriving at Mercury is only half the battle. Surviving there is another. Sunlight at Mercury is up to 11 times stronger than on Earth. Temperatures swing from 450 degrees Celsius in sunlight to 180 degrees Celsius in shadow. Spacecraft need advanced sunshades and insulation just to survive. MESSENGER used a ceramic sunshade to protect its instruments. Electronics must be specially shielded against intense solar radiation. The BepiColombo mission takes this even further, with dual orbiters and cutting-edge thermal protection. These missions are engineering marvels, built to withstand an environment that would destroy ordinary machines. Mercury pushes our technology to the limit. MESSENGER's journey to Mercury was a masterclass in patience and precision. Launched in 2004, it took 7 years and 6 planetary flybys to slow down enough for Mercury's gravity to capture it. Each flyby, Earth, Venus, and Mercury itself, was a carefully timed braking maneuver. The spacecraft had to pass its destination 3 times before finally entering orbit. Every pass gathered valuable data, but the main goal was always to shed speed. In 2011, after nearly 8 billion kilometers, MESSENGER finally entered Mercury's orbit. It was a triumph of orbital mechanics. Reaching Mercury is a journey of endurance and ingenuity. Mars, by contrast, feels almost welcoming. Its journey is more direct, its environment less extreme, and its mysteries deeply compelling. Mars may have once harbored life, its ancient riverbeds and ice caps hint at a wetter, warmer past. We send rovers to search for biosignatures and clues to planetary evolution. Mars is a laboratory for understanding Earth's history and future. Its day is similar to ours, and it has resources for potential human settlement. The dream of colonizing Mars drives exploration forward. Mars is more than a destination. It's a vision for humanity's future. The journey to Mars is a model of efficiency. We launch into a higher orbit, timing our path to intersect Mars's. This Hohmann transfer takes just 7 to 9 months. Mars's atmosphere allows for aerobraking, using friction to slow down, not fuel. This lets us land larger, more capable rovers, and even helicopters. Shorter travel means less risk and faster scientific returns. Mars missions are sprints, fast, direct, and packed with discovery. It's a mission profile that keeps the cadence of exploration steady. So why does Mercury take 7 years and Mars just 7 months? It's all about energy, not distance. Mars lets us coast outward, Mercury forces us to fight the sun's pull every step. The difficulty of reaching Mercury is a testament to the extremes of our solar system. Each mission pushes the boundaries of science and engineering. Every planet presents unique challenges. There's no one-size-fits-all solution. The solar system is a puzzle, each destination a key to new knowledge. Our curiosity drives us to tackle these challenges, no matter how daunting. The contrast between Mars and Mercury reminds us, exploration is never easy, but always worth it. Let's keep reaching for the stars, together.